So here's a review question involving Laplace transforms. Laplace transforms are useful for solving linear ODEs with constant coefficients. We're asked to do two things in this example. Firstly, we're asked to prove a result, and secondly, we're asked to calculate this particular transform. Now, actually, part I is used in part II. Okay? Now, just to refresh your memory, the Laplace transform is an integral transform. So you've got some function, little f of t. You take that little f of t, you multiply it through by an exponential, and you form an improper integral. Now, the dummy variable here is s. So here we're integrating with respect to t. So the s is going to be left over. And this is why sometimes we write the Laplace transform as a function of s. And just to kind of, I guess, try to keep the notation clear, capital letters, big F of s, usually refers to the Laplace transform of the lowercase letters, little f of t. So, proof directly from the definition that if this is the Laplace transform of little f of t, the Laplace transform of t times little f of t is just negative big F prime of s. So for this one, what we're going to do is start with the definition and differentiate to kind of form the right-hand side of the thing we want. Okay, so I think I can fit it in down here. So we differentiate, we're forgetting about the thing in the middle for the moment. We're differentiating both sides of star with respect to s. Now, how do we simplify this bottom corner? Well, we can differentiate under the integral sign by applying Leibniz rule. Okay, this is a reasonably simple case, and for our purposes, we can sort of imagine that we can just move the DDS inside the integral sign and change it to a partial. Now, the reason that we change it to a partial is because what's in here is a function of two variables, s and t. Okay, so here we've used a special rule called the Leibniz rule. All right, well, let's look at the partial derivative of this with respect to s. Well, f of t is not going to do anything, but e to the minus s of t, st, what's going to happen there? Well, imagine the t is a constant, and differentiate with respect to s. So the minus t is going to come to the front. Now, if I just clean it up a little bit, let's take the minus sign out to the front. Or actually, let's take the minus sign over to the other side. Okay, we've got equality here, so and if you look carefully, maybe I can just bracket it. Let's compare this with what's up here. Well, these are the same except for this t. So what we've got here is actually not the Laplace transform of little f of t, it's the Laplace transform of little t times little f of t. So we've now proved that our identity holds. Okay, so the key for this is Leibniz rule. Differentiate under the integral sign, and then you can form a useful identity. Now the second part of this question involves producing or calculating the Laplace transform of 4t times sine 3t. Now you can probably do that a few different ways, but if you look up here, I can actually use the identity I to calculate the Laplace transform of this, because it's t times another function of t times 4 sine 3t. So let's use what we've just proven in part I and see if we can quickly compute this, the transform of this. Okay, so here we've got the following. So think of little f of t in this context to be 4 times sine 3t. You could do the calculations just using sine 3t and then multiply everything by 4, but I'm not going to do it that way. So what we want to do is take the Laplace transform of this, okay, so what this means is, from a practical point of view, first of all, let's get big F of s by calculating the transform of this 4 sine 3t. Then we'll differentiate that with respect to s and then just multiply it by -1. Okay, what is this Laplace transform? Well, you could work it out directly, but we usually use a table. So if we look down here, we get to sine bt. Well, we want the Laplace transform of sine 3t. So you would go over here and just replace b with 3. Okay. Now I can bring that 4 out the front if I want to, because Laplace transform's a linear operator. So here I've used a table and I'm saying so. So now what I want to do is, in order to produce this, I want to take what I've got, differentiate it with respect to s, and then just multiply it by -1. Okay, so if I differentiate this with respect to s, well, I'm going to get something like a minus 2s on the front, on the top, sorry, from there. So that's going to connect with this. I'm going to get minus 24s on the top, and I just square the bottom. Okay, so to use this, I just want to change the sign here. And this is just the Laplace transform. Okay?